Welcome back. We made a formal beginning of Newton's laws of motion, the dynamics. I already gave you a detailed account of the three fundamental laws of motion given by Newton, and I think I did give an explanation of each of those laws and made a very categorical statement that the second law is the most fundamental law, and we didn't leave it at that. We tried to derive the first law from second law and the third law also from second law. So the theoretical background I gave it to you in my last class. Today we go rather deep into this, but then there's going to be a slight deviation the way I'm going to handle the remainder of the classes. For example, when I start with the most fundamentals of the forces, what are the number of base forces that we have in nature? See, forces, there are only three. One, gravitational. Two, nuclear, strong force. Three, electro-weak force or electromagnetic force. It's called plus beta decay weak force. In fact, these two are combined now. For a long time, the research is on in the world to prove that all the forces are one only. These are all manifestations of those forces. In the process of proving that, this is the latest of the things that I think way back in 1979, it's hardly around 41 years. Professor Abdus Salam, with whom of course I had the great opportunity to be with him for some time, he was the man who published a paper combining that beta decay force is nothing but a manifestation of electromagnetic force, reducing the number of fundamental forces to 3, not 4. Remember, you may call it as electromagnetic force or you may call it as electroweak force. It makes no difference whatsoever. And one, of course, gravitational force. Now, if you say what is the source of this gravitation, nobody could give a plausible explanation so far, except that of Einstein's, whose way of stating and the understanding of that, I think, is rather rare. Maybe at this level it's really difficult to understand what he was saying. He said it was essentially due to the curvature of the space that the so-called gravitational force arises. But what Newton thought of was it was a sheer mass that is the criteria. But whatever it is, we all experience gravitational force, right? And what we don't see is nuclear strong force. It's confined to when a bomb explodes, the nuclear bomb explodes, or in a nuclear reactor we do come across, otherwise we never talk of this. But that leaves us with only two types of forces to handle. Well, gravitational force is, I can't discuss all the details of gravitational force at this stage, except that if you place a huge body, a planet or star or any huge body, any body, and then you have its mass is capital M, its mass is small m, and if the distance between these two, and this is the radius of the planet, and this is the force of attraction between these two magnitude-wise is gmm by r squared, the force of attraction. And if this force is equated to, although this also gets accelerated, being a huge mass, its acceleration is negligible. We consider this to be stationary, but if the masses are comparable, that also we must take into account. I'll discuss that at a later date, but definitely I'm going to talk about that point. So, but since it is due to gravity, this is given a symbol called G. Therefore, your Gm by r square is equal to G. Okay? Now, if you talk of very close, if h is far less than r, you may take it as gm by r square, that is equal to g naught. And this is fairly a constant value when you go up to around, say, 10 to 30 kilometers or 40 kilometers above the surface. So virtually we take it as constant, whose value approximately you can take it as a 9.81 meter per second square. Mind you, it does indeed vary from point to point, from height, from depth, everything. All those associated details will be discussed in great detail when we talk of gravitation. For the purpose of this study, that is not required as of now. So we would accept that the G value is that, and gravitational force would always act vertically down. That's how we will accept it, okay? Right. Now that leaves you with, as I said, electromagnetic forces. What are these electromagnetic forces? Every force that you talk of is nothing but an electromagnetic force, as I said, excepting gravitational and excepting your nuclear storm force. If somebody slaps somebody, that's a magnetic force, the electromagnetic force. Wherever you rub something, we come across friction, gravity, electromagnetic force. Tension is electromagnetic, tensile force is an electromagnetic force. Normal force is electromagnetic. In fact, almost all forces that we talk about in our day-to-day activity, barring gravity, are virtually electromagnetic forces. Of these things, we will discuss in great detail about 3 or 4 forces. They're all manifestations of electromagnetic forces only. Starting with the first one, tensile force, or simply tension. That is number 1. Number 2, spring force. Number 3, normal force. Number 4, friction. We will discuss these things in great detail while dealing with, say, tension or something. I'll be making use of Newton's second law, or I'll be using the integration technique. You must be prepared for that. But before I go into this, the application of Newton's second law I will give you in a very, very simple manner, presuming that 2 bodies are connected and I am applying a force M1 on body 1 and force F on body M1. No other force is acting. This is pulling this. So as far as this is concerned, this is pulling in this direction. So when you want to apply Newton's second law, always draw what we call as a free body diagram. That means you sketch out a body, put with an arrow all the forces acting on the body, and then resolve them into components, sum it up, and equate it to that to solve. I'll tell you, for example, I take this body, what are all the forces? I'm ignoring all except horizontal, because FBD I will discuss separately for you. On this side here, if this is a wire, maybe a force tension that is acting. Here it is M1. Let me presume that it is accelerating with here. There is only one line. So, all in the direction of acceleration of forces I take, that is only F. All opposite, there is only one T. So, F minus T, this is your net force, net external force. And this is equal to mass times acceleration. This is how I am going to apply Newton's second law. Now look at body number 2. This body number 2, as far as this is concerned, tension will pull it away like this. There is no other force acting. I said I'm not talking of vertical forces here. Just the application of Newton's second law on horizontal direction only I'm showing. Therefore, here external force is only T. Therefore, T is equal to M2A. So I have derived two equations based on Newton's second law. How many variables? A is a variable, right? T is a variable, F is known, is already given. You have to solve using your simultaneous equations technique. If I add these two, I will get M1 plus M2 into A, or A is equal to F by M1 plus M2. Therefore, T is equal to M2A. Likewise, so I found out A, I found out B. Likewise, we work out Newton's second law, right? I will be using that in discussing these forces in detail. Number one, first, we look at the tension. See, you take a tension, generally comes across in rods, wire, rope, chains, etc. Rods, what is the difference? What is actually tension? It is the internal restoring force. Whenever you try to stretch it. Now, I talk of mostly inextensible. If it is extensible, elastic forces will come into play. Say, for example, spring. Spring is also a form of elastic force only. I am going to confine my attention as far as tension is concerned to inextensible. For example, here is a rod, rigid body. If I am applying a force here, every part of it is being pulled in this direction. That means wherever you have that force that is acting, you can pull it. Or if I remove this, I can push the body. This is pulling the body. Remember, I am talking of rod. So, tension can be a pulling force or a pushing force as far as rigid rods are concerned. As far as wire, rope, chain, etc. they are concerned, it is bound to be only a pulling force. I need not have to mention that every time I speak about. You should understand that it is going to be pulling. Why? If I try to push it, this gets slackened. So there is no question of tension to be a pushing force as far as wires, ropes, chains are concerned. Remember this. That's number one. Next, tension is represented as T and it acts both ways. What do you mean by that? It at a point, this may be same, may be different. It is possible. It could be same, it could be different. Alright? Now, when you say tension acts both ways, that is very important point. Tension is a pulling force as far as the flexible bodies are concerned, like chain, wire, rope. Okay? Now, the next one is first point. Pulling only for chains, etc. Pulling or pushing for rods. 3. It acts both ways. Always away from the body in question as far as ropes, chains and wires are concerned. Always away from the body, right? Next, for massless chains, T is same everywhere. For massless chains, T is same everywhere. If mass of chain is considerable, if mass of chain is considerable, then tension differs from point to point. Tension differs from point to point. It's very, very important. Every time we talk of, you should bear all these facts in mind. Now, when does tension arise? When does tension arise? Tension arises only when an unsuccessful attempt is made to stretch it. Remember, tension arises only when an unsuccessful attempt. I am trying to stretch this wire or chain or rope. When I do that, I should not be successful. Why? Because the very definition of our rope and this is inextensible. Therefore, we go by this, and that attempt to stretch will result in this. Suppose you are successful, what will happen? String will break. Strings, chains, ropes, wires, etc. It will break. So I am talking of, that is actually, if you apply too much of that force, the intermolecular forces cannot withstand. At one stage, they give up their fight and the whole thing is broken. Okay? So that is what we call as breaking tension, breaking limit. So when we talk of ropes, chains, wires, strings, we mean when we apply the stretching forces within the breaking limits. Okay? So unsuccessful attempt to stretch it, because you know you can't stretch it. And if there is no attempt to stretch, there is no tension. That's very important. Now I'll tell you. For example, I take a rope. Let us say its length is some 10 meters. What is the tension in the rope now? If I ask you, I am now considering massless. Actually, it's useless to talk of massless. The fact is that you have only less mass cases. In other words, the mass of the wire is negligible. Then we talk of. So we take virtually that the mass is not considerable. Therefore, tension is same everywhere in the rope. Okay, that's number one. Number two. Are you making any attempt to stretch it? No. Therefore, it's in a slackened position. Tension is zero. Fine. Now, I am now bringing it to its natural length. I am bringing it to its natural length. What is the tension everywhere? Again, zero. Why? There is no attempt to stretch it. I now take it. No complications when I am considering. Whenever you apply force on the wire, rope, chain, string, etc., if you apply the force, it may come along with you. That means it is able to accelerate the body. Okay? That's a well-known thing. But That is not concern with us. That doesn't concern with us because my interest here is how much stretching is done on this. Now look at this. If I ask now, the wrong answer is T is equal to F. Suppose I am applying 10 newtons there. What is tension here? 0. Why? All the 10 newtons is used to accelerate the body. All the 10 newtons is used to accelerate the body. Therefore, there is no attempt because if mass is present, that mass will resist. Now we consider no mass, so there is nothing, no resistance is offered by the body. Therefore, any force that you apply that is going to accelerate the body, right? So we have got like therefore tension is 0. It's a very important case, mind you. Very, very important case. So this is 0. Now, next, I am applying force F. I am applying force F here. Both sides I am applying the force. What is the net force on this body? Plus F minus F, 0. Okay? Now, how much force is it? Now, what is happening to both the forces? Now it is trying to stretch it. It's not able to stretch. But how much of attempt to stretch is made? Here no attempt to stretch is made. That's why tension is 0. Here if I am applying 100 newtons and I am applying 100 newtons here, then with all 100 is used to stretch unsuccessfully. Therefore T is 100 or T is equal to F. Obviously your acceleration is 0 because net force is 0. Slacken position tension 0. Straighten position tension 0. Straighten position F is applied on one side, tension is 0, there is no mass. But I apply force on both sides, same magnitude, opposite direction. I am now making an attempt to stretch it, that's why the tension is 100 newtons. Or I mean, if it is 100. Otherwise, F. Now look, I am now fixing one end and applying, say, force F. What does it mean? As long as this is fixed, this is applying, if this is F, this will be F automatically by the wall or whatever, wherever you have tied it to. Okay? Therefore, it's similar to this problem. So tension is F here. No acceleration at again. Now I go a little deep. Now look, I'll give you a numerical, it is better. 100 newtons. Suppose I am applying 90 newtons there. What is the net force here? 100 minus 90. That is 10 newtons. 10 newtons is the net force. Therefore, it will accelerate, no doubt. But what is this force that is attempting to stretch it? 90 newtons is used to stretch it. 10 it's not doing. So the amount of stretching is 90. Therefore, tension is 90. Now, look at this. Suppose this is 100 and this is 80. What is tension? 80. You go on 100 newtons and this is 15 newtons. Then tension is 50. Not 100 minus 50. 50. Okay? Now, if I go on increasing this force on one side, I may come to 100 newtons here, 100 newtons here, tension is 100. Suppose I am taking 110 newtons and this continues to be 100 newtons. Tension is 100. What is it you have understood from this? It's a massless body, inextensible body. Only the attempt to stretch it will result or it manifests itself as tension. Therefore, whichever is less is your tension. Whichever is less. This is a very, very important point. Now, I'm going to make a statement. If it is a massless rope or wire, T is same everywhere except when it runs over a heavy or rough pulley, because pulleys are also problems for us. If I take a pulley and this is rough or same wire, tension is not same on both sides. If it is heavy, this has mass, this has friction, then this will be T1, this will be T2. Mind you, same massless rope, but still tensions differ if it passes over a rough pulley or a heavy pulley. You understand? Otherwise, tension remains the same. Okay? Right. Now, supposing I take a heavy pulley. I am taking a heavy pulley. Means what? I am applying a force F1 here. I am applying a force F2 here. Total length of the rope is L. I probably want to get tension at a distance x from, maybe I'll write 1, it will be clear. Tx is, okay, I need not take 1 here, 1. From end 1 where F1 is applied, from the end where F1 is applied. That is the meaning of it. First I'll do this with integration approach. Okay? What I do here, consider a small elemental rope of thickness dx. Let this tension be dx, or rather t, and let this be t plus dt. Okay? All right. If I presume that it is accelerating like this, remember in integration, if my x begins like this, increases, that parameter also should increase. In fact, if it decreases, you will get a negative automatically. Okay? Now, here, what is the net force acting on the body? I told you, tension acts both ways. It pulls both sides. Now, this is how it is accelerating, therefore, this force minus this force, opposing force, that is equal to mass of this element is dm into acceleration. You know, generally, if it is a linear wire or rope, we define a linear density called lambda dm by dx. Lambda equal to dm by dx. This is what I am going to use throughout our mechanics classes. If it is a 2D body, mass per unit area, I'll call it as sigma density. And if it is a 3D body, mass per unit volume. This is how I'm going to use standard throughout. I may use these things for other purposes as well. But for as far as these are concerned, density, this is what I'm going to do. Okay? Now, what do you get here? The dm, I can write it as dm is equal to lambda dx, isn't it? So I will write here a lambda dx, and this is minus dt. You got this? So minus dt is a lambda dx. Now, what does it mean to us? See, minus dt is a lambda dx. All depends on, is your lambda a constant? Now I will take case 1, lambda is constant. I am taking constant. That means I can directly integrate this. Minus dt is equal to a lambda integral dx. From where to where? x0 corresponds to tension F1. Any general x corresponds to Tx. Therefore, how do I write this? Integral dt is t. This is F1 Tx and this is a lambda 0 to x. So Tx minus F1. There is a negative sign. Therefore, F1 minus Tx is equal to a lambda x. That is number 1. Now the same thing, if I apply my limits as F1 here, F2 there, a lambda x 0 to L. You know that wire x0 here, x is equal to L, their tension is bound to be F2. Okay? Now if you substitute this, a lambda L, right? Now it's right. Now use these two equations and divide them. A lambda gets cancelled. So you have x F1 minus F2 is F1 minus Tx into L. I bring it onto this side, and minus Tx, if I bring it, it will be Tx. I will retain F1 here. If the whole thing goes minus x by L, F1 minus F2, I can write F1 into 1 minus x by L, minus minus plus F2 into x by L. This is Tx1. Look, this is a very, very important relation. The tension x1 stands for x from point where F1 is applied. Likewise, I have put it. Suppose if it is Tx2, you will write F2 into 1 minus x by L plus F1 into x by L. That's how you are going to write. From this you can find out if x is equal to 0, this will cancel, T becomes F1. If x is equal to L, this becomes 0, this becomes 1. Tension is F2. That's how we have started out. All this is valid when it is a heavy row and constant density, linear density. Possible sometimes they may give you, what if the lambda varies? So, I will write it here. Tx1 is F1 into, I am writing it in such a form so it is easy for you. You look, I have applied the limits twice. One for the extreme values, one for a general value and a known value, so that you can directly find what is of interest to you. Okay? Now this is case 1. We will go to case 2. What is case 2? Lambda is equal to kx. Say for example, from 1, the density is increasing. What do you mean by that? What is the length? Length of the rope is L. What is the mass? How do you do that? dm is equal to lambda dx, right? What is lambda? kx dx. This is dm. So now you are in a position to integrate it. 0 to L, 0 to M, this is M is equal to x dx, x squared by 2, 0 to L, you get KL squared by 2. This is the mass. This is the mass you should understand. Okay? Right. Now, our interest is tension. So, how? We have taken as before, minus dt is equal to A lambda dx. That is common to both the cases. T on one side, T plus dt on this side. Net force is this. Got it. But what is lambda? Kx. So, now I can integrate it. While integrating here, I am telling you known values. X0, Tf1. If x is equal to L, this is F2. I write again. F1, A, K, 0. This is x. This will be dx. Here it is x dx. With the same integration, apply two different sets of limits. One both known values, in the other one unknown value which we are interested to work out. That is why I am considering it like this. How do I write that? You already did this before. With negative sign, I get like this. AK into x squared by 2 is L squared by 2. What about this? F1 minus Tx, AK, this is x squared by 2. As before, if I divide these two, all these things gets cancelled. F1 minus F2 into x square is F1 minus Tx into L square. What am I getting? L square, I bring it onto this side. So Tx also, as before, I bring it onto this side. F1 will remain minus x squared by L square, F1 minus F2. So you get F1 into plus F2 into, this is a very important result for you. You see how it is easily influencing the end product. Alright? Now, what is that? When is this valid? Lambda is constant. When is this valid? If lambda is equal to x. Let them give any value. This is the procedure. First I took lambda constant, then I took lambda is equal to kx. You may take next lambda is equal to ax plus b. Anything is given, you please try to go ahead with this only. Is the procedure all right for you? Right. I have used that integration there. The other one that you can avoid, second method. I use that first method. Now here I have F2 here, F1 here, X here. What is this? L minus A. What is the mass of this? L minus. What is the mass of this? What do I do? This whole thing I treat it as one body whose mass is X lambda. This point I imagine a light rope there, and the remaining part I take it as another body. So here are two bodies, because I am interested in T here, and I am applying F1 here, applying F2. How do I do that here? Now you see, If I draw only for horizontal, I have F1 T. So this implies F1 minus T is equal to M1A. What about the second body? Now this is T, this is F2. So this implies T minus F2. L minus X lambda A. You divide the two equations, lambda A gets cancelled. Now you rearrange and write, you are going to get this answer. But always get used to using the technique of integration. That is very important. Okay? Right.